So if you think back to the example we did in the last video where we had to actually make a graph of, we're just going to talk about the error bound, the third derivative, to figure out what the behavior of the third derivative is, to find out some sort of upper limit on it. This is how that idea might actually show up on the AP test when we get to part C of this question. So check out part A. You don't see this problem too often where they give like a giant table of values with a bunch of derivatives, but it comes up occasionally. Part A asks us to write the first degree Taylor polynomial for h about x equals 2, and then use that to approximate h of 1.9. So just notice, first degree Taylor polynomial. First degree means degree 1, x to the first, linear. It's the same thing as the tangent line approximation. So you could write this polynomial, or you could use tangent line approximation notation. Either one would get full credit. The first degree Taylor polynomial should have, evaluated at x equals 2, is going to have h of 2, which is 80, plus the first derivative of h, evaluated at 2, I'll write h prime of 2 times x minus a to the first, divided by 1 to the first. And then I would stop here, because this has x getting raised to the first power in it. This is the first degree Taylor polynomial. So I can rewrite that. I know in this case, about x equals 2 means that a, in this case, equals 2, and I know h prime of 2 is 128. So I'm going to write my tangent line approximation. I'm going to write it using Taylor polynomial notation. The first degree Taylor polynomial, which is a function that I can plug an x into, is the first number is going to be, the first term is going to be f of 2, or h of 2, plus the first derivative, 128, times x minus 2 to the first, all over 1 factorial. So this is, I could say that p, I've been asked to use this approximation now to find h of 1.9. So h of 1.9 is approximately equal to p sub 1 of 1.9, which equals 80 plus 128 times 1.9 minus 2. Notice this answer gets full credit. This happens to be the calculator section, so you could simplify this. You can simplify this without a calculator if you want to. This is your final answer to an approximation for h of 1.9. Is this approximation greater than or less than h of 1.9? So this is a tangent line approximation. Whether this tangent line approximation is an overestimate or an underestimate has to do with whether h itself is concave up. So I know that the function h and its first 4 derivatives are increasing. So if h is increasing and h prime is increasing, h prime is increasing, that tells me the second derivative of h is positive, because the first derivative is increasing. The second derivative is positive, then h must be concave up. I make myself that picture. Here's a concave up function. Here's the tangent line approximation. It's an underestimate. So that's how I would type of my reasoning. My estimate is an underestimate because h prime of x is increasing on the interval 1 to 3 inclusive. All right, my next job, part B, is to write the third degree Taylor polynomial. So if I got this far, this far in the first degree, I probably have remembered the pattern, and I'm going to write the third degree Taylor polynomial. I see I did not give myself lots of room. All right, we'll get by. So the third degree Taylor polynomial is going to be for h at or about x equals 2. That's going to be the actual function value plus the first derivative times x minus 2 to the first plus the second derivative, that's 488 thirds times x minus 2 squared over 2 factorial plus the third derivative, which happens to be the same, that's interesting, 488 thirds x minus 2 cubed over 3 factorial. This is the third degree Taylor polynomial. Notice my notation, p sub 3 of x. I haven't replaced x with anything. If my next job is to use this Taylor polynomial to approximate h of 1.9. Notice I'm going to write h of 1.9 is approximately equal to p sub 3 of 1.9, which is, and then I'm going to write this polynomial with all my x's replaced with 1.9. I'm going to go to a cleaner place so I have room to do that. Okay, so two good pieces of news. You have no obligation to simplify your answer, and this happens to have been on the calculator section problem, so feel free to use your calculator. I'm going to write this out, the 80, that's an 80, get nicer, 80 plus 128 times 1.9 minus 2 is negative 0.1 to the first over 1. I just got excited. You don't have to actually write that over 1 plus, I might multiply this out. I know 2 factorial is 2, so I'm going to multiply by my denominators, 488 over 6 times 1.9 minus 2 is negative 0.1 squared plus 488. 3 factorial is 6 times 3 is 18, negative 0.1 cubed. I could have simplified that even less and still received full credit. It turns out if you type this into your calculator, you're going to get 67.988 to 3 decimal places. Again, feel free to leave this as your answer on the AP test. All right, now it's time for Part C. Part C asks us to use what kind of like that big idea for this section is what can I say about the error in my approximation from Part B. So we've been asked to use the Lagrange error bound, that's that same error remainder estimation theorem that we've been talking about, to show that our answer from Part B is wrong by at most 3 times 10 to the negative 4th. So let's flash back up here. Remember what we know. So the error, the difference between our estimate made with the third degree Taylor polynomial and the actual value of h of 1.9 has to be less than or equal to, and that we use the third degree Taylor polynomial. That's the Taylor polynomial that comes from using all the derivatives up to the third derivative. So in this case, n equals 3. So this expression that we're going to write looks a lot like what the fourth term would look like. This part's exactly like the fourth term in the Taylor polynomial, but instead of having the fourth derivative of h evaluated at 2, I find some sort of upper limit for the fourth derivative, and I'm going to use that for my m. So I'm going to be able to write this expression. It's absolutely true. All I'm going to have to do next is to do enough math here to prove that this is less than, what was it, 3 times 10 to the negative 10th. All right, so I'm going to start by writing that expression. Whoops. The remainder, well, the absolute value of the remainder. That's another way of saying the error. And the error is the difference between the thing I was looking for, which was h of 1.9, and my answer, which came from using p sub 3 of 1.9. So the reason I'm writing that instead of capital R sub n of x, we haven't defined in this problem that R to mean anything specific. So I'm just writing an expression for the error, the difference between the actual answer and my answer, the absolute value of that difference, instead of having to stop and define what R means. This is the common notation you would see. This is the notation that they're going to publish in their answer key. Is going to be less than or equal to the decision I have to make here. The one decision I have to make is what I'm going to use for m. I need an upper bound on the derivative, on the fourth derivative of h, on the interval between my a, which in this case is 2, and the x value that I've been asked to evaluate at, which is 1.9. So what I ask myself is, on the interval where x goes from 1.9 to 2, what is the maximum value of the fourth derivative of h? So I can actually tell, I can find an appropriate upper bound because I've been told that all the derivatives that we've been told about are increasing, which means they hit their maximum value at their right-hand endpoint. So on the interval, I might say on 1.9 is less than or equal to x, which is less than or equal to 2. The max, that's not official notation, but we could use that. The max of the fourth derivative of h is 584 ninths, because the right-hand side of that, the right-hand edge of that interval is 2. So at 2 is where the fourth derivative is going to have its maximum value. So once I've made this decision, I'm going to go back, I'm going to rewrite my error statement. I'm going to move this out of the way so I have more room. And then remember, my goal is to prove that the expression I write is actually less than 3 times 10 to the negative fourth. I'm going to write the absolute value of the difference between h 1.9, the actual h of 1.9, and the answer I gave in part 3 has to be less than or equal to, this is going to be capital M. I decided I'm going to use 584 ninths. 584 ninths divided by, n in this case was 3, so n plus 1 is 4 factorial, and this is x minus a, in this case is 2, raised to the 4th power. So I'm grateful that this is the calculator section. I'm going to type some of this in. That's 584 over 9 times 4 factorial is 4 times 3, 12 times 2 is 24. The x I'm using, oh, this should be absolute value. 1.9 minus 2. To the 4th. I'm going to use my calculator to evaluate this. So I've evaluated that. That turns out to be 0.00027, which is in fact less than 0.0003. So I might just conclude that h of 1.9 minus p sub 3 of 1.9 is less than or equal to, this was 0.002703, which is less than 3 times 10 to the negative 4th. There you go.